With the preliminaries out of the way, we are now ready to get started on the derivation of Maxwell's equations. The first step is to define the math we will use for our analysis. It is postulated earlier that in the absence of disturbances, an ether exists throughout all of space that is homogeneous, isotropic, and incompressible. In this rest condition, it is possible to divide the ether into small volume elements, or cubes, and label each cube with the coordinates of its center. R is equal to x, y, and z. We can then analyze the motion of this ether by looking at the deviations from this equilibrium condition at each point. Said in simpler terms, we can look at each one of the cubes and watch them move over time. Both the cube of the negative ether and the cube of the positive ether can move independently. Here we will define the vector p to be the position of the positive ether cube relative to its equilibrium point. P is equal to the position of the positive ether minus the equilibrium value for its position, which is its position xyz minus its original position r. Simply put, the magnitude of p is the distance that the positive ether has moved away from its equilibrium position, while the direction of p is the direction it has moved away from its equilibrium position. For the negative ether, similar considerations apply, and we will define the vector n to be the position of the negative ether cube relative to its equilibrium point. At this point, it is again useful to attempt to picture what is meant by the mathematical constructs just discussed. Since the ether is proposed to be a solid lattice occupying all of space, we can of course divide it up for analysis into volume elements of any shape we wish. Earlier we looked at a small cube of the ether, but here we see that the ether is divided into cylindrical shells. The picture shows a cross-section of the shells, and in the dimension perpendicular to the drawing, nothing changes. Each shell shown here has the same amount of area. Without any sources or sinks, both the vector p and the vector n that were just described are zero everywhere, since none of the ether has been disturbed. But were we to inject a cylinder of detached positive ether into the central region labeled number 1 here, then the ether that was originally in the central cylinder would be pushed outward to the next adjacent cylinder. Similarly, the ether that was in cylinder 2 would be moved to cylinder 3, and that was in cylinder 3 would be moved to cylinder 4, and from cylinder 4 to cylinder 5. You can think of this as being similar to placing a cylindrically shaped water balloon into a bathtub full of water. The water in the balloon will push the bathtub water out of the way, moving the bathtub water out radially. In the ether model, we are envisioning placing a cylinder of detached positive ether into our attached ether C, and it will move the attached positive ether radially outward. In this ether model, there are two such C's, and this action would leave the negative ether with all of it being in its original place. So the vector n will still be everywhere 0 as a result of adding the detached positive ether. But the vector p is now no longer 0, and in this case the vector p is inversely proportional to the distance from the center of the cylinder once we are outside of that cylinder. This result comes from the fact that each cylinder has the same area. Since the area of the cylinder for a small difference in radius, delta r, is 2 pi r times delta r, it can be seen that keeping the area constant means that delta r must be proportional to the inverse of radius. Putting a cylinder of free detached ether into the attached ether thus moves the attached ether radially outward in a way that is inversely proportional to the distance from the disturbance. For one specific example, let's look at the situation at the boundary of the inserted attached ether. At that point, the magnitude of p is equal to the radius of the inserted ether, since the attached ether at that point has been moved from the center. The direction of the displacement is radially outward from the center. The attached ether has been moved radially outward by a distance equal to the radius of the inserted ether. For ether that was originally at the edge of the first section, it moves radially outward to the edge of the second section, and so on. For this example, we see that P always points radially outward, and the magnitude drops off as 1 over the distance. In general, we will not have this situation where the detached ether is a perfect cylinder, and there may be detached negative ether as well as detached positive ether. But the important point to understand is that the attached positive ether will move by a distance p depending on the insertion of sources of free positive ether, and the negative ether will move a distance n depending on the insertion of a source of free negative ether. Additionally, waves within the solid may also cause the ether to move away from its equilibrium position. To sum up, P of x, y, z, and t is the vector field that describes how far positive ether originally at a point x, y, z, and 0 has moved away from that point at time t, while n of x, y, z, and t is a similar expression for the negative ether. As a result of the fact that we are assuming that the ether is incompressible, we just saw how detached pieces of ether will push the adjacent attached pieces away from their equilibrium positions. Here we see a picture of 2 cubes of ether. One is an undistorted cube of attached ether, which is delta x wide by delta y high by delta z deep. Note that if a substance is incompressible, the density of the substance is always constant. Hence, if we now add an amount of free detached ether to the first cube, the size of the volume must expand in order to keep the density constant. The second cube shows such an expanded volume. In the second cube, the width is increased by an amount epsilon x, with the height and depth increased by epsilon y and epsilon z. Now the amount of attached positive ether in the second cube is equal to the amount of attached ether in the first cube, since all we did was to pour in some extra detached ether, and that gives rise to the first expression in equations 2. Of course, the density of anything is equal to the amount of it divided by the volume it occupies. The original density, which is the density in the small cube that has no detached ether, is called rho sub 0. The amount of the attached ether in the larger cube is the same amount that it had before it was expanded, which is rho sub 0 multiplied by the volume of the original cube. The volume of the larger cube is expressed in the denominator to give us the density of the attached ether in the larger cube. Now, it will generally be the case that the amount of attached ether is far greater than the amount of the detached ether, and so the epsilon quantities are very much smaller than the delta quantities shown here. This allows us to make the first of the approximations shown in equations 2. In the first approximation, the denominator is expanded by keeping only the first-order terms in the small quantities. In the second step, the numerator and denominator are each divided by the volume of the original cube. The last approximation uses the fact that 1 over 1 plus epsilon is approximately equal to 1 minus epsilon, resulting in a rather simple equation for the density of the attached ether in a region where there is some detached ether immersed within it. Continuing on with our derivation, the picture and the result from the previous slide appear again at the top of this slide. We now need to resolve the quantities epsilon x divided by delta x, epsilon y divided by delta y, and epsilon z divided by delta z. Recall that the vector p is the displacement of the attached positive ether with respect to its equilibrium position. Hence, the x component of p at x is the displacement of the left yz face of the cube shown in the picture. It's displaced from where it originally was to where it becomes later. And that the x displacement of the yz face at x plus delta x is p sub x evaluated at x plus delta x, y, z, and t. P sub x, evaluated at x plus delta x, is how much that the right face gets expanded into the next cube. Hence, epsilon x is given by P sub x, evaluated at x plus delta x, minus P sub x, evaluated at the original point x. And epsilon x divided by delta x then becomes the familiar expression for the partial derivative of P sub x with respect to x. As we take the limit, delta x goes to 0. Since the divergence of P is defined as follows, if we repeat this analysis for the other adjacent faces of the cube, we will obtain that the density of the attached ether in the expanded cube is given by rho sub 0 times 1 minus the divergence of P for the positive ether. And repeating the analysis for the negative ether will give us rho sub attached negative ether, the density of the attached negative ether, will be the rho 0, our normal equilibrium density, times 1 minus the divergence of n for the negative ether. The result from the previous slide has been copied to the top of this slide. As a final step in analyzing the effect of incompressibility, note that incompressibility means that the density of the attached ether in any volume plus the density of the detached free ether will always sum to rho sub 0. Hence, we can manipulate equations 3 by bringing rho sub 0 times the divergence of P over to the left-hand side of the equation, and then bringing the density of the attached ether back over to the other side of the equation, and then dividing through by rho 0. This results in the expressions shown here. We then make note that rho sub 0 minus the density of the attached ether is equal to the density of the detached ether. Lastly, we can recall equation 1 from our vector calculus review and substitute the divergence of P into those expressions to find that the Laplacian operator applied to psi sub P is equal to the density of the detached ether divided by the uniform ether density. These equations will be quite important when we make an identification of Maxwell's equations later in this webinar. Indeed, equations 4 are the central important ramification of our postulate that the ether is incompressible.